Alright, hello everybody. This video is going over the practice questions in the textbook for Reactivity 1.1. The first question says, when equal masses of X and Y absorb the same amount of energy, their temperature rises by 5 degrees Celsius and 10 degrees Celsius respectively. Which of the following is correct? So in the question, they're talking about mass, amount of energy, temperature, and in the answer choices, they're talking about specific heat capacity. So you should know that they are talking about the relationship in the equation of Q equals MCAT. Now in this equation, it says that there are equal masses and equal amount of energy, which means Q is the same in both and M is the same in both. Since all of the answer choices are talking about specific heat, we can rearrange the equation to solve for C. Now to make this easy in my head, I just sub in the value of 1 for Q and for M for both X and Y. So if I was solving for the specific heat of X, I would have a Q of 1 and a mass of 1. And since X has a temperature change of 5, I would sub in 5 there. And for C of Y, I would do the same thing, but again, I have a temperature change of 10, so I would use that. Now for my specific heat of X, I would get 0.2, and for my specific heat of Y, I would get 0.1. Now you could do this entire thing with reasoning, but I just wanted to show you how to get it with the math in case that was easier to understand. So as you can see, when we solve for this, the specific heat of X is twice that of Y, so A would be the final answer. A pure block of aluminum with a mass of 10 grams is heated so that the temperature rises 30 degrees Celsius. The specific heat capacity of aluminum is 8.99 times 10 to the negative first. Which expression gives the heat energy change in kilojoules? So like we talked about in class, I do want you to start noticing the units right away because these questions are very prevalent. So when we get a question that's asking us, what is the expression in kilojoules, and we know that we're given in joules, we know that our answer has to be divided by 1,000. So that means automatically you can cancel out both A and B as options. Right away, that gives you a 50% chance of getting the question right. So for this question, we are looking for our heat energy change, which is Q. So we're going to be using Q equals mc delta T. We know for Q that our mass is 10 grams. Our C is the specific heat, which was 8.99 times 10 to the negative first. And our change in temperature was 30 degrees Celsius. Remember, we can just use that in exchange for Kelvin because it's a change in temperature. So the change in degree is the same in Celsius and Kelvin. And then we are going to divide that by 1,000 because we are currently in joules and we want to get to kilojoules. So this would be our expression here, which is going to give us D as the answer. Two 100 centimeter cube aqueous solutions, one containing 0.01 moles of NaOH and the other containing 0.01 moles of HCl, are at the same temperature. When the two solutions are mixed, the temperature rises by Y degrees Celsius. Assume the density of the final solution is 1 gram per centimeters cubed. The specific heat of water is 4.18. What is the enthalpy change of neutralization in kilojoules per mole? So we know we're solving for enthalpy change, which is delta H. And we are given a lot of information that points us towards the Q equals MCAT. So we know we're going to use Q equals MCAT and then use Q in our final equation, which is delta H equals negative Q over N. So the first step is solving for Q. So if we were solving for Q, we know that our mass total would be 200 grams, and that's because the density is 1 gram per centimeter cubed, and the mass of each solution would be 100 grams. So if we add those together, that gives us a total of 200 grams. And then we know our specific heat is 4.18 that was given to us. And our change in temperature would be Y. Now, this right now as it stands is in joules because of our specific heat. So we need to divide this number by 1,000. And now we have Q. So to solve for delta H, we need to have our moles. And since we are talking about enthalpy change of neutralization, we need to look at what we have in this reaction. And the reaction between NaOH and HCl is going to produce salt and water because it's a neutralization reaction. So let's go ahead and write out our balanced chemical equation. So you can see on the bottom we have our balanced chemical equation. There are no coefficients, which means everything is a 1-to-1 ratio. So if we have 0.01 moles of NaOH reacting with 0.01 moles of HCl, that means we're going to have 0.01 moles of water. And now that we know that's going to be N in our equation. So if we're keeping with the expression, we would have 200 times 4.18 times Y divided by 1,000 and divided by our moles of water, which is 0.010. So that would give us our final expression of B. Okay, so questions 4 and 5 are both going to be geared around this combustion of ethanol using water and a thermometer and a beaker. So we are measuring the change in temperature of the water or the heat absorbed by the water. So when we are solving for enthalpy of combustion, we first have to solve for Q, which is the amount of energy absorbed by the water, which is why we are using the mass of water and the specific heat of water. So in solving for Q, we need our mass of water, which is 100 grams. We need our specific heat of water, which is 4.18. And we need our change in temperature, which is going to be 10 because it went from 20 to 30 degrees Celsius. Now our specific heat was given to us in joules, and we want our answer in kilojoules per mole. So we know we need to divide this number by 1,000 in order to get our heat absorbed in kilojoules. So then we need to solve for our enthalpy of combustion. Now we are solving for combustion. So what are we combusting? We're combusting ethanol. So now that we have the amount of heat that is absorbed by the water, we need to solve for the enthalpy change of ethanol. So that means when we're solving for delta H equals negative Q over N, the N is the moles of whatever you're combusting, or the ethanol. So I wrote down delta H equals negative, and then I put in Q. Now we need to solve for N. So in order to solve for moles, we have our mass of ethanol, which is 0.23 grams, and we have our molar mass of ethanol, which is 46.08. Now you should know at this point, in order to go from grams to moles, you need to divide by molar mass. So if we wanted the moles of ethanol, it would be 0.23 divided by 46.08. So that's going to be in the bottom, or the denominator of this equation. So it would be 0.23 divided by 46.08, and that would give you your moles in the denominator for the question. And with that, you get your answer choice of C. Now, just to circle back to this, when we are looking at the question and the answer choices at the very beginning, remember it's asking you for kilojoules per mole and you're given joules. So we can automatically cancel out D because it does not divide by 1,000. And then if you look at A, it gives you a temperature change of 10 times 273, which is not temperature change in this equation. It is 20 to 30. So that should also be an easy one to cancel out. So again, you're left with a 50-50 chance of the correct answer. Number 5 says which quantity is likely to be the most inaccurate due to sources of error in the sink experiment. So let's go through our answer choices. For the mass of ethanol burnt, the mass is going to be measured by weighing the burner before and after the experiment. So while there may be a slight inaccuracy due to the evaporation of ethanol, the mass measurements of a balance are usually pretty accurate. So then going to B, the molecular mass of ethanol, this is a fixed value. It's 46.08 grams per mole. So it does not contribute to experimental error. So B would not be the correct answer either. And then the mass of water. The mass of water is going to be measured based on volume and assuming that it has a density of 1 grams per centimeter cubed. So since the volumes are easy to measure with a graduated cylinder or a pipette, that's not going to be a major source of error. Now if we get to D, your temperature change, it's going to be measured using a thermometer, and there are going to be many factors that are going to introduce inaccuracies. So we have the heat loss to the surroundings, which is going to reduce the actual temperature rise. We also have inconsistent stirring, so that could be uneven heating throughout the water. Another thing could be your thermometer precision, which can introduce some error. And lastly, we also have heat that's going to be absorbed by the beaker instead of just the water. So those are many inaccuracies that could be due to temperature change. So D would be the correct answer in this situation. Number 6 says methanol is made in large quantities because it is used in the production of polymers and in fuels. The enthalpy of combustion of methanol can be determined theoretically or experimentally. A says the enthalpy of combustion of methanol can be determined experimentally in a school laboratory. A burner containing methanol was weighed and used to heat water in a test tube, as illustrated to the right. The following data was collected. AI says calculate the amount in moles of methanol burnt. So we know to solve for moles, we need our mass given and we need the molar mass. That can also be illustrated with this equation as well. So first, using the data given to us, we need to find the mass of methanol that was burnt. And we have our initial mass of the burner, and we have our final mass of the burner, so we can get the change of that, and that's going to be our mass in grams of methanol burnt. So if we take 80.557 and subtract 80.034, that's going to give us a mass of 0.523 grams. And then our molar mass of methanol is 46.08 grams per mole. So when we divide that, it's going to give us 0.01135 moles. And if we are looking at sig figs here, which would be 3 because of these two numbers, that would give us a final answer of 0.0114 moles of methanol. So the second part of A says calculate the heat absorbed in kilojoules by the water. So it's going to be using Q equals mc delta T. So we are solving for Q. We have a mass of 20 grams of water. Remember, when we're getting this heat absorbed, it's the heat absorbed by the water. So we're looking at the mass of the water, the specific heat of water, and the change in temperature of the water. So everything is about the water. So we have 20 grams. Then we have our specific heat of water, which is 4.18. And then we have our change in temperature of 4.9, which again, it's just the initial or the final minus initial temperature. So it'd be 26.4 minus 21.5, and that gives us 4.9. And then finally, don't forget to divide by 1,000 because our specific heat is in joules and it's asking for kilojoules. So that's going to give us a Q of 0.410 if we're going to 3 sig figs like in our question, and that would be kilojoules. So now the third part of A says determine the enthalpy change in kilojoules per mole for the combustion of 1 mole of methanol. So to solve for enthalpy change in kilojoules per mole, we already have our kilojoules, which is Q, and then we need to solve for our moles, which again we already solved for in the first part of A. So it would be 0.0114. That's going to give us a delta H of negative 36.1 kilojoules per mole. And the negative is going to tell us that it's an exothermic reaction, which in a combustion reaction is standard. B says the data booklet value for the enthalpy of combustion of methanol is negative 726 kilojoules per mole. Suggest why this value differs from the value calculated in part A, which was negative 36.1 kilojoules per mole. So our experimental value for the enthalpy of combustion was much less exothermic than the data booklet value, and that is going to be because of several factors. So the first one is going to be your heat loss to the surroundings. Some heat is going to be lost to the air. It's also going to be lost to the test tube and to the thermometer instead of being fully transferred into the water. Also, the setup is not perfectly insulated, which is going to lead to a lower measured temperature change, and that's going to affect your final enthalpy of combustion. Another factor would be incomplete combustion of methanol. In that experiment, the incomplete combustion would produce a carbon monoxide and soot, which would collect the bottom of that test tube. The result would be less energy being released compared to complete combustion, which would again lower your value for enthalpy change of combustion. The final thing I would explain would be the heat absorbed by the equipment. The beaker or the test tube is going to absorb some of the heat, which is not accounted for in your calculations. Number 7, the data below is from an experiment to measure the enthalpy change for the reaction of aqueous copper 2 sulfate and zinc. 50 centimeter cubed of 1 mole per decimeters cubed copper 2 sulfate solution was placed in a polystyrene cup, and zinc powder was added after 100 seconds. The temperature time data was taken from data logging software program. The table shows the initial 19 readings. A straight line has been drawn through some of the data points. The equation for this line is given by the data logging software as t equals negative 0.05 t plus 78, where t is temperature and time is lowercase t. So A says the heat produced by the reaction can be calculated from the temperature change using the expression below. heat change equals the volume of copper 2 sulfate times the specific heat capacity of water times delta T. Describe two assumptions made by using the expression to calculate heat changes. So here we're looking at the volume of copper 2 sulfate for our Q and the specific heat of water. And so we're not talking about the heat that is absorbed by the zinc or the heat that is absorbed by the cup. Those are not in your calculations. So those would be the first two things I would think of, and since it asks for two assumptions, that's what I would describe. But we could also talk about that the assumption is that all of the heat was transferred to the water and the copper 2 sulfate. We also could talk about the assumption that the density of the solution is 1. And then the other thing we could talk about is that the temperature is uniform throughout the solution. So those would be all the assumptions that IB chemistry would take for the mark scheme for this question. B says use the data presented by the data logging software to deduce the temperature change which would have occurred if the reaction had taken place instantaneously with no heat loss. So the reaction occurred when they put in the zinc powder at 100 seconds. So if it occurred instantaneously, that means it would have occurred at 100 seconds. Now, if we were to read the graph, that would give us about a T final of 73 and a T initial of 24.8, which was given to us in this original data here. So then that would give us a delta T of 48.2 degrees Celsius. Now for the second part of B, it says state the assumption made in the first part. And the key assumption is that the reaction occurred instantaneously and no heat was lost to the surroundings, which means that all the heat generated by the reaction was fully transferred to the solute, which was idealized because in reality, some heat is going to be lost to the environment. And then the third part of B is calculate the heat in kilojoules produced during the reaction using the expression given in part A, which is heat change equals volume of copper 2 sulfate times the specific heat of water times the change in temperature. Now for our mass, we are assuming that the density of water is 1 gram per centimeters cubed, which means our volume of 50 centimeters cubed of copper 2 sulfate solution would be equal to 50 grams. So that would be our mass in Q equals MCAP. Then we have our specific heat of water, which is 4.18. And then we have our temperature change of 48.2. Lastly, it does say that we need to go from joules to kilojoules, so we need to divide this number by 1,000. That is going to give us a Q of 10.1 kilojoules, which we are going to leave in 3 sig figs because all of our data given to us is in 3 sig figs. The color of the solution changed from blue to colorless. Deduce the amount in moles of zinc which reacted in the cup. So we know that 1 mole of copper 2 plus reacted with 1 mole of zinc. So the moles of zinc reacted are the same as the moles of copper 2 sulfate. So if we are solving for moles of zinc, we can use the moles of copper 2 sulfate that are given to us to get the same answer. So we're going to use our concentration equals moles over volume, which means to solve for moles, we would have our concentration times our volume. And our concentration is 1 moles per decimeters cubed. And our volume is 50 centimeters cubed or 0.05 decimeters cubed. So that's going to give us a final answer of 0.0500 moles of zinc reacted. All right, 8 says calculate the enthalpy of neutralization based on the following data. It gives you your initial and final temperature of the solution. It gives you your concentration of your acid and base, and it also gives you your volume of your acid and base. So first, when we're calculating enthalpy of neutralization, we need to first get our Q, or our heat absorbed. So that's going to be Q equals MCAT. Our change in temperature is going to be 30.3 minus 24.5 from the data given. Our mass, since we're using water and our assumption is that it is a density of 1, we can take our 50 centimeters cubed of each, add them together, that would be 100 centimeters cubed, which equals 100 grams if your assumption is that the density is 1. And then our specific heat of water is 4.18. So now that we have that, we can go ahead and solve for Q by multiplying them together. That gives us 2,424.4 joules. And volume, we can go ahead and solve for moles of our KOH and moles of HCl. So if we were to solve for moles of our KOH and HCl, we would get 0.0475 moles of KOH and 0.0525 moles of HCl. Now, since we have a 1-to-1 ratio in our balanced chemical equation, we know that KOH is going to be our limiting reactant, so we're only going to have 0.0475 moles of water. That is going to give us a enthalpy change of negative 50.9 kilojoules per mole. And there are several assumptions that we have made in this calculation. The first is that the specific heat capacity of the solution is the same of water. The other assumption is that the density of the solution is 1 gram per centimeters cubed, which is the same as water. And another assumption is that no heat was lost to the surroundings. Okay, so now we are moving into the practice questions in the textbook for reactivity 1.2. It says consider the following reactions. What is the standard enthalpy change in kilojoules for the reaction below? Now we want copper solid as a reactant and right now as a product. So we're going to go ahead and flip this reaction, which means we now have copper plus copper 2 oxide reacting to form copper 1 oxide. And that means we're going to flip this sign, so now it's negative 11 kilojoules. And then up here in the top equation, we can go ahead and see if everything cancels out and we have what we want. Our copper 1 oxide is going to cancel out completely. Our copper 2 oxide is going to cancel, so now we have only 1 on the right, and now that gives us our final equation below. So all we had to do was combine these two enthalpies. So we have negative 144 plus negative 11, which also is signified by 1. Negative 144 minus 11. So C would be your answer. 2. Which equation best represents the bond enthalpy of HCl? So bond enthalpy is going to be the energy required to break 1 mole of a bond in a gaseous molecule into its individual gaseous atoms. Now when we're talking about bond enthalpy, remember we are talking about the dissociation of a single H to Cl bond into separate gaseous H and Cl atoms. Now for our first option of A, it shows the ionization of HCl. This is going to be ionization and not bond dissociation, so A would not be the correct choice. Option C, this is going to be incorrect because it implies the formation of diatomic molecules rather than individual atoms, which is not what we're looking at here. And same with D, it's going to represent the formation of diatomic hydrogen and chlorine molecules. And again, here we're only looking at the breaking of one HCl bond into its gaseous atoms, which would be B. Three says consider the equations below. What is the enthalpy change for the reaction? So this is another Hess's law equation. Now in order to get my final reaction, first I need to look at what I'm given. So I need to get 2 moles of CH4. Right now I only have 1, so I'm going to multiply this by 2. So this is now 2x. Then I need oxygen gas, which I have a lot of that, so I'm actually going to move on and save that for the end. So then I'm looking at my COOH2, and that is a product. And I already have that over here, so I'm going to leave that be. Then I have 3 molecules of H2O, and I currently have 2 here and 1 here, so I already have that. So now I'm going to go back to my oxygens. So if I have to get a total of 3.5 oxygens, I already have 2 here and a half here. So if I multiply this entire thing by 2, that gives me a total on the left of 3.5 oxygens. And now I just need to make sure everything cancels out correctly. So my HCHO would cancel out on both sides, and my HCOOH would also cancel out on both sides. So I'm left with 2 moles of CH4. Then I'm left with 2 plus 1 is 3 plus a half is 3.5. So I'm left with 3.5 oxygens. And then I have 1 COOH2, and I have 2 waters here and 1 water here, which gives me a total of 3 waters. So now I'm good. So I have to combine all of my standard enthalpies. So I have 2x plus 2y plus z, which is going to give me C as my final choice. 4 says which process has an enthalpy change that corresponds to the bond enthalpy for the O to H bond. So remember from a previous question, the bond enthalpy is the energy required to break 1 mole of a specific bond in a gaseous molecule into its individual gaseous atoms. So for the O to H bond, the bond enthalpy is going to correspond to breaking 1 O to H bond in water into separate H and O atoms in the gaseous state. Now for this one, A and C can automatically be canceled out because that is liquid water, and when we're talking about bond enthalpy, it only is corresponding to gaseous molecules. So A and C with the liquid water would be completely canceled out. Then we are looking at the options of C or D. Now in option C, that's going to represent the complete dissociation of 1 hydrogen and half an oxygen atom, but bond enthalpy is defined per single bond and not the entire molecule. So since we're looking at a single bond, that means we're looking at the bond between H and O. our final answer would be D. Five says, what is the energy in kilojoules released when 1 mole of carbon monoxide is burned according to the following equation? So we have negative 564 kilojoules that are released. Now, since 2 moles of CO releases 564 kilojoules, in order to find out how much is released by 1 mole, all we would have to do is divide this by 2, which gives us our answer of negative 282 kilojoules. Now this says how much energy is released, so the negative is already implied, so it's saying that 282 kilojoules are released, which is what this negative means. So the answer would just be 282 kilojoules of energy. Number 6, which enthalpy changes cannot be calculated accurately using only bond enthalpy data? Now this question is rather simple because with bond enthalpy, remember, it has to be gaseous molecules. So in 1 and 2, they both have a liquid molecule, which means enthalpy changes cannot be calculated. So the answer would be A, 1 and 2 only. Hydrazine is a valuable rocket fuel. The equation for the reaction between hydrazine and oxygen is given below. Use the bond enthalpy values from section 12 of the data booklet to determine the enthalpy change for this reaction. So remember, when we're talking about enthalpy change of reaction using bond enthalpy values, we're going to be looking at bonds broken minus bonds formed, or the bond enthalpy of your reactants minus the bond enthalpy of your products. So if we're looking at the hydrazine molecule that has 2 N's and 4 H's, that means we are only going to have a single bond between the 2 nitrogens, and then we have 4 nitrogen to hydrogen bonds. So if we're looking at that, and then we're also looking at our O2 molecule, if we add up all of the bond enthalpies from these 2 molecules, that's going to give us positive 2,220. And then if we look at our bonds formed, or our reactants, we have N2, and we have 2 waters, so that's going to be H2O. So if we add all of those together, that's going to give us negative 2,797. Those are both in kilojoules per mole. So if we are looking at our total enthalpy change, it'll give us a total enthalpy change of negative 577 kilojoules per mole.